So as we look at polar coordinates, I'm going to try to pull in some prior knowledge for you, knowledge of the Cartesian coordinate grid system, which is your normal XY system, knowledge of the unit circle, knowledge of vectors. None of those are what a polar coordinate is, but at least they help you make some sense of a polar coordinate. So for instance, if we were to start, and I'm just going to plot up here, the ordered pair 3, 4. If I asked you to plot the ordered pair 3, 4, here would be your Cartesian coordinate grid, right? And you would go to the right 3, and you would go up 4. And you would plot a point right here. And that point right there would represent the point 3, 4. There is only one place in the Cartesian coordinate system that represents the point 3, 4. It means go to the right 3 and up 4, period. There's no other way to describe that ordered pair. And this is a point that is plotted on a flat plane, right? Do we live in a flat plane world? What if I need to describe a point that's on a curve? Or a point that's in space? We live in a three-dimensional universe, do we not? So polar coordinates make rectangular measurements easier in problems. So we need to be able to convert from rectangular to polar and vice versa, and we need to understand what polar really means. And so a polar coordinate just means a way that I can name something, that same point 3, 4, but in a space or on a curve or just in a different way, perhaps based upon a problem that I'm trying to solve. And we'll get more into applications of polar coordinates later, but right now we need to really understand what is a polar coordinate. So as you look at this right here, let's talk about the parts of a polar coordinate grid system. And so this point here, we're going to call 0. It's not really 0, it's O. And that O is the pole. The pole is what you used to know as 0, 0, the origin. So that's why we're going to call it O. And this line right here, which used to be the x-axis or the initial side of our angle in the unit circle, this is called the polar axis. And then from here to here, the opening of that theta, that's our directional angle. And so that's nothing new to you. That makes sense. Then we have this distance from here to here. I'm going to call this point right here point P. And this distance to point, this distance to point P is R. And so let's put point P in there as well. You used to know R as magnitude on a vector, right? R is a distance. R is your radius in the unit circle. So it looks very similar to those things in the polar coordinate system. And then this point P, this polar coordinate, what you used to view as X is now R, the radius that we're rotating about. And that theta is our directional angle. So just like a magnitude, a polar coordinate has direction and magnitude. So just like a vector. But this magnitude, this R, it's called it's a directional distance. It can be negative this time. Negative just means it tells you what direction it goes. Negative doesn't have any other reference to it other than that. Are there any questions on that? You might want to also note that this is your polar coordinate. Any questions on the pieces of the polar coordinate grid? Because you'll get a lot more. The hard part for you today is going to be to name all the possibilities for a polar coordinate, and you'll see why in a minute. So before we go through that, let's just talk about the different parts here. So R is known as your directed distance. So this is the directed distance. So directed distance from O to P, and of course the point P can change to any letter of the alphabet. Whereas theta is equal to the directed angle and theta can be in radians. If you're not writing this down, my question is why? Because you can't know what I'm going to write before I write it. Radians is, oh my goodness. It's really hard to write small with this little thing. So radians or degrees. They're called directed angle, directed distances. Well, as I said before, that r can be negative, so we have to talk about what that means. If r is greater than 0, doesn't that mean that r is positive? So if this directed distance here is positive, a certain thing occurs. And what you're about to write is going to make absolutely no sense to you. But write it right now, and then when we start plotting this, it'll start to make more sense. But I need you to write it down first. So if r is greater than 0, then P, which is our polar coordinate, then P is on the terminal side of theta. And what I would like you to put there in parentheses is that you would actually move forward. And you'll know what that means in a minute. However, if r is less than 0, meaning that r is negative, then P, which again is the polar coordinate, is on the terminal side of theta plus pi, and that'll make sense to you momentarily. And in this instance, when r is negative, technically it means that we will be moving or move backwards. And you'll even hear me kind of give you the visual that instead of moving backwards, what that means is that we will shoot through the pole. That's a technical term, shoot through the pole. So as soon as you have that written down, we're going to actually flip to the back of your notes. And so you might want to write yourself a little note jogger here. See next page first, or for your purposes, see the back of your notes. I'm going to put on here, see next page first. See next page first. So we're not going to do example 1 yet. I'm going to do a pre-example 1. Does everybody have that written down so I can put a blank page up there? So right now, you know nothing. But you're going to keep referring to this. All right, so I'm going to add a blank page. All right, so we're going to start example 1. So we're back from that second blank paper that we just were dealing with. And so let's move our paper up. And we're only going to get through example 1 today. So we're going to plot these, and we're going to talk about all the possibilities. So let's go ahead and plot this point here, P, at 2 pi over 3. So we're going to focus on pi over 3 first. So we want to plot that angle first, and you won't see me putting the circles in at this point. So here's your polar axes. And then pi over 3 is what angle measure? 60 degrees. And what quadrant is that in? So this is 60 degrees or quadrant 1. I'm not going to be picky that, oh, you drew a 30-degree angle. I'm not going to be picky about that. So what we are going to do is I'm going to draw an angle that goes from here to about 60 degrees. But I'm going to draw an entire line that goes all the way through here. That represents that line that's been rotated. So we're just taking this line right here and we're rotating it all the way up so that this part comes back down. So if I had a 60-degree angle, it might look like this. And I'm going to draw it as a dashed line because from here to here, this is theta, which is pi over 3. So what that means is that my polar coordinate P is somewhere along this line here. Well, isn't R positive? So we're not shooting through the pole, right? So if I go from here to here, isn't this the positive part of my line? So that means that P is actually somewhere along here, and it's a distance of 2, because we're not shooting through the pole. So we're going to plot it a distance of 2. So here might be a distance of 1, and this would be a distance of 2. So I'm plotting my point right here and naming it P. There it is. But if you were asked to name all the possible, and you can see here an example too, the directions, find all polar coordinates for P. If I asked you to find all polar coordinates for this right here, well, we're going to do that based upon what we just learned. So start with your original polar coordinate, 2 pi over 3. And then from here, 2 pi over 3 puts me here. Can't I just add or subtract full revolutions to get back to that same point? Right? So then for me, you're going to be adding or subtracting 2n pi. For Math Excel, what are you doing? You're just putting the plus in there, right? So that's one set of your possibilities. Then for the second set, we're going to change r to -2. We still start with pi over 3, but let's think about this. If r is -2, well, my theta is pi over 3, but the -2 is going to shoot me through the pole and put me over here, won't it? But I want to get back to over here, so don't I have to add the pi? And then I can add full revolutions from there. And Math Excel, it looks like this. So we're going to add, and then another set of parentheses. Then it'll be 1 plus, 2n, and then another parentheses, pi, and then end your parentheses. So it's 1 plus 2n pi. That represents the additional pi plus all the revolutions of 2 pi that you might end up putting in there. And so these become all of your possibilities for that polar coordinate. Any issues with that? We're going to keep doing it. Repetition, repetition, repetition. So let me put a squiggly line through here. All right, so then let's go ahead and plot Q. Q this time has a -r. And it's got the angle 3 pi over 4. What degree is 3 pi over 4? Not 270. Not 115. Well, wouldn't pi be 4 pi over 4? And pi is 180, so that has to be less than that. So doesn't this have to be in quadrant 2? So first of all, this is quadrant 2. And what is the reference angle? 45 degrees because it's over 4. And then if you take 180 and subtract 45 degrees, don't you get 135 degrees? Or you can just convert it using 180 over pi. But you need to know what quadrant you end up in, because here are my polar axes. If theta is 135 degrees, here's my initial side. I'm going to go from here to 135 degrees, which puts me in quadrant 2. So this is the front half of my line right here. So from here to here represents theta of that 3 pi over 4. But I need to look at the other end of this line as well, because it really extends in both directions. My polar coordinate can be anywhere here or here. Because this is the terminal side of theta, this is the terminal side of this line, is this part right here in quadrant 2. If r is positive, then my polar coordinate would be plotted here. But r is negative. Because r is negative, we're going to shoot through the pole and we're going to end up being plotted down here. There's no such thing as a positive or negative quadrant anymore. It's all about where's the terminal side of theta, and then is your r positive or negative. So if that r had been a positive 1, we would have plotted a positive 1 right here. But because it's negative, we're reflecting it across the origin, shooting it through the pole, and it lands right here. So our actual point would be, this would be, let's say, for chuckle's sake, a distance of 1, a radius of 1. And so that's our point Q, right there. Let's name all the possibilities for Q. The easiest is always the first one. You start exactly as your ordered pair looked. So even though my r was negative, we still stick with a negative 1. And then our theta was 3 pi over 4. So we stick with our original theta. And then from here, so this is my theta of 3 pi. We shot through the pole to get to negative 1, so here's that point. Then from here, I just have to keep adding revolutions, full revolutions, to get to that point. So I'm going to add here, or subtract, because I could subtract full revolutions. So I'm going to add or subtract 2n pi. Sierra, did you have a question? Are you good? So for your first set of possibilities, it's always 2n pi. Your second set of possibilities, what are we going to do to r? Change its sign so it becomes positive. We still keep the 3 pi over 4. And then you are going to add, there's not a plus minus on that one. Technically there could be, but we're not going to go with that one. And then you're going to add a 1 plus 2n times pi. And remember what this does is, this right here, it adds to theta, it adds a pi, and then however many full revolutions. Because if you distribute the pi, there's your pi right here that we're adding. So we're adding a pi to that. Because if I go from here to here, there's your 3 pi over 4. If I have an r of 1, that means we stayed here. So in order to get back over here, I have to add pi to it, and then we can add the full revolutions or subtract the full revolutions. So this right here adds the pi, and this right here adds the full revolutions of 2n pi. Any questions about that? Is it making more sense? All right, let's see you do C. What's the little catch with C? It's given in degrees, which is okay. We can have that. So now we like that because we think better in degrees, right? And what's the other catch? It's negative. Well, that's all right. Theta can be negative. We know what to do with a negative degree, don't we? Here are our polar axes. What direction do we go for a negative 45? If this is our initial side, do I go counterclockwise or do I go clockwise? Clockwise. And so what quadrant is negative 45 going to end us up in? Yep, so this is going to be quadrant 4. And so this would be my line here, and then this right here, from here to here, would represent a theta equaling negative 45 degrees. So what that means is that if I'm going clockwise, this is now my terminal side of theta. So if r is positive, it's going to get plotted on this side. If r is negative, we shoot through the pole and we'd be plotting over on this side because technically my line continues infinitely in that direction as well. So is r positive or negative? Positive. So we're going to go from here to here. That's our negative 45 degrees. Because r is positive, we're going to plot point R on this side of the line. And we're going to go a distance of 3. So this might be a distance of 1, a distance of 2, and this is a distance of 3 right here. So that represents point R. I want you to write down what you think all the possible polar coordinates for R could be. I'm just using these right here, but you got to know them. I won't give them to you. First one's always easy. All right, so what are we doing for our first? Keeping it the same. This one's a little bit tricky. It's a little different, and I actually didn't test this out on MathXL, but this is 3 negative 45 degrees. And then we would be adding or subtracting not 2 pi, but what? 360 degrees n.
So if it's in degrees, you want to keep it in degrees?
Yep, if it's in degrees, you want to keep those revolutions that you're adding in degrees. So what are we going to do instead, degree-wise, for this? This out here is going to be what? 180. So won't this stay the same?
Yeah.
And that's the part I haven't tested with MathXL, so we'll have to check that out. But what do we do with our R? Your R changes sign, so your R becomes negative 3. The negative 45 stays the same. You're going to add parentheses. It still remains 1 plus 2n. Whoops. Will you let our little intruder in, please? Times, instead, 180 degrees, and then end your parentheses. And that'll represent all of our possibilities. So since I have time, we're going to go to example 2. You just have to watch the last part of this video. All right, so any questions on that before we move to example 2? Yes?
Well, how come you didn't change the 2 to 360?
There's no need. If you distribute, the 180 becomes your 180 degrees, which is your pi, right? And if I multiply the 180 to the 2n, don't I get 360n, which is what that is. So they're going to want it, if they want it in degrees, they're going to want it to look like that. Because that's what 180 plus 360n is going to have in common anyway. They're going to have 180 degrees as a greatest common factor. And all I did was change the pi to 180. Does that make sense? Yeah.
Like I see the pattern of changing from like 2 to negative 2, but why does it do that?
So let's look at this one. Let's just look at this one that we just did. So if I stick with this one right here, to go a negative 45 degrees, we went down or clockwise, right? And then because R is positive, this is our terminal side, our angle got plotted on that side of it. So I want my answer to be right here always. When we change R to negative, when we go from here to here, that's the terminal side of theta. But the fact that R is now negative 3 shoots us across the pole over here. I don't really want to be there because technically R could be negative. We have to consider that possibility. So if that's a possibility, then I need to add or subtract technically, but we're always going to add. I'm going to add to negative 45 degrees. I'm going to add a directional change of pi. Because if I change this direction 180 degrees, won't I end up over there? Even though my theta was negative. So let's add 180 degrees to 45. What does that give us? If we add 180 degrees to 45, what does that give us? Well, it's negative 45. So what would that be? 135 degrees. So technically, the 45 plus, this is going to represent 180 degrees, our theta turns into 135 degrees because 180 plus negative 45 is 135. Doesn't that represent 135 degrees right there? So if I went from here to here, there's my terminal side of theta. But now my theta is negative 3. So now I'm going to shoot through the pole, and won't I end up where I want to be? So that's what this is saying, is it knows that, okay, because this is negative, I'm going to end up shooting through the pole and getting over here. So I might as well get myself up high ahead so that when I shoot through there, I end up where I want to be. Because if I don't add that pi, if I just go down here to negative 45, I'm going to shoot through the pole this direction, and I don't want to be there. But if we add 180 degrees from the very beginning to negative 145, we actually end up with a positive angle of 135, and then when we shoot through the pole, because our r is negative, we do end up where we want to be. So it just takes some getting used to thinking in those terms. All right, so let's try 2. Example 2. So if p has the polar coordinate points of 3 pi over 3, we're going to go ahead and plot that. So here's our polar axis. Our theta is pi over 3, so what angle measures that? 60 degrees. So let's go ahead and plot a line that is 60 degrees. So it might look like this, going from here to here. So from here to here, my theta is equal to pi over 3. But I always like to extend the line just in case we have to shoot through the pole. Now, is our r positive or negative? It's positive. So as I rotate theta, pi over 3, because r is positive, this is the terminal side of the line. So won't point P be plotted here? And we will not be shooting through the pole. Agreed? Right? So I need to go a distance of 3. So here's my distance of 1, distance of 2, here's a distance of 3. So I'm going to plot my point right here, P. And so that point in that polar system is represented by 3 pi over 3. But they want to know all the possible coordinates. So we start off with our original 3 pi over 3. Well, then what do I do? Plus or minus what? 2n pi. So that gives us half of our possibilities. Then what do we do?
Negative 3.
Change your sign of your r. Do I keep theta or change it?
Keep it.
Keep it.
And then plus.
And then plus,
Parentheses 1.
parentheses 1.
Skip 1.
Technically it's plus or minus. 2n times pi and n. And then these represent all of our possibilities. And you can just kind of test it. You can kind of test it by giving n a value and then adding or subtracting. Yes?
So if we forgot to put like plus or minus on the test,
I'm not going to mark you off for that just because, but well, you know, I might actually, because I really need you to understand that we can subtract. Because I can't help that your publisher doesn't do that. Technically, it's allowable. And we'll run across some of those as we look at them.
Can you?
So as you look at your first page of notes, when I went through Math Excel, this second piece right here, they won't accept it in this order, which is really ridiculous. They will only accept it if the 2n comes first and the 1 comes second. Ridiculous but true. So we're going to correct something. We are going to correct this to read 2n plus 1, and in my world it's plus or minus 1, right? Because in my world we do plus or minus. Math Excel just does a plus. So technically it's a plus or minus, but only put the plus in for Math Excel. And then it still has the pi at the end, but they won't accept 1 plus 2n. They should, because addition is commutative and it shouldn't really matter, but they will only accept 2n plus 1. Yes?
So is every plus in the equation plus or minus?
Except for this one's just a plus.
Oh,
Now technically, could you add or subtract a pi? Yes, but let's not go there. So only for the parts here that you're adding the full revolutions that count, we're going to do plus or minuses there. If for some reason you put a minus there, it probably wouldn't mark you wrong, because technically you're not incorrect. But we're just going to leave that as a plus. So then over here, we're going to correct this one to read 2n plus 1. And then over here, we're going to correct this one to read 2n plus 1. It's a minor correction. And of course, down on example 2, we have to do the same thing. We need to correct this to read 2n plus 1, right?
What's the difference between 1 plus 2n?
There is no difference, which is my irritation with MathXL. And of course, there's a plus minus in all of these.
Then I can just leave it as 1 plus 2n.
No,
right now.
MathXL will not accept it. That's what I'm trying to tell you.
Oh, well, I said I'm going to write a note and get it on.
Oh, okay. Yeah.
So,
Well, because they probably wouldn't take it last night. So if you were trying to do this particular problem here, and you put it in the original way, they're going to give you an error message. And the only difference is that they wanted this to read 2n plus 1 versus 1 plus 2n, which is stupid. I will grant you. Sam?
And I missed yesterday, but so the reason you're saying the full revolution is because you're finding every time it's
Correct.
null with that.
Right. Because we can go infinitely. Polar coordinates, we have infinite number of
It already tells
possibilities.
you, you just plot it and say,
Yep. So then go to the back of your notes, which was for Peter's sake. Okay, hang on. And the directions for this one will be plot the polar coordinate. And so I'll start off with example smiley face. I can't exactly use A and B because that's an example 1. And so this example, we're going to plot the polar coordinate 1, comma, pi over 2. And here's a big hint. Huge hint. So write your hint right here. Big hint. When we plot polar coordinates, you want to find theta first. Double exclamation point, double underline under first. So we don't start with r first, we start with theta first. And so in this case, 1 is my r, and pi over 2 is my theta. So I'm going to draw, and these will probably be the only 2 examples you'll see me drew a true polar coordinate grid system. But I'm going to draw my axes. Of course, you'll use a ruler. Mine are ever so straight.
Can you say r equal to x?
No, don't. Yes, technically it's your way of thinking r is x, but it has nothing to do with what you view as the x-axis, which is here is the polar axis. So I wouldn't view it in that term. We will view it that way later for other purposes, and we'll keep pulling in prior knowledge for you to think that way, and so if it helps you to think that way, that's fine, but it doesn't work the same as a Cartesian coordinate system, which we call rectangular because we move in a rectangular distance. We go up, down, and right, left, which creates rectangles. So that's why you'll see the Cartesian coordinate grid called rectangular coordinates. This is polar. Now, technically, a polar coordinate will look like this, where you have like these, it's hard for me to make a dotted line, so you'll have like these circles that have radiuses coming from O. And so the first circle's right here, this is a radius of 1, this would be a radius of 2. Well, this would be a circle with a radius of 3, and they're usually dotted, so you can dot yours. It's really hard for me to dot mine. This would be a radius of 4, and so forth. And then we have angle markers coming through here. What angle do you think that would be? Coming from this being the terminal side to that angle, 45 degrees. And that's what I've drawn, 45 degrees. And so this would be angle what? 30 degrees. And then this would be angle what? Nope, this one right here. Has to be bigger than 45. 60. And I can do that in all quadrants. And granted, there are numerous angle markers that I could draw. But I'm just drawing our special right triangle markers. So if I want to find theta first from 0, and let's see, I'm thinking I'm going to use a blue arrow. So from here, I start at 0, 0. This is my terminal side right here. I'm sorry, my initial side. It's our polar axis. This is where we always plot our directional angle. So if I'm going to go pi over 2, what degree is pi over 2? Not 180. 90, right? So I'm going to go from here, somewhere along here, I'm going to go from here all the way up to here. Agreed? So that means that somewhere along this line here, my polar coordinate is going to end up. So let's go ahead and mark this as, let me get a blue in here. This is our pi over 2. So that's where pi over 2 is. So that means that my angle of direction, my directional angle, goes from here to here. That means that theta from there to there is pi over 2. So I know that somewhere along here lies my polar coordinate. My polar coordinate has an r of 1. Well, if I went from here to here and landed on this side of this line, and I'm just going to make that line a little darker by giving it some color. So I think maybe I'll give it some color. I'll give it like a salmon color. So here's my line right here. Somewhere along this line falls my polar coordinate. Somewhere along that line. If I went from here to here, and this is where you need to kind of flip back to the front of your notes where we wrote if r is positive versus if r is negative. So from here to here, I'm landing on what is called the terminal side of theta. Isn't this the terminal side of theta and this is the initial side of theta? So this is the terminal side of theta. If r is positive, I'm going to plot my r on this side of this whole line. If this had been a negative r, we would go from the terminal side of theta and shoot through the pole onto this opposite side. And your polar coordinate would end up on this side of the line. So a negative for r means that we're shooting through that pole onto the opposite side of where we ended up. And for instance, how far is it from here to here directionally? What is 180 degrees? So when I said that r was negative, what did I say? Well, when r is negative, I said you'd move backwards.
Yeah.
Right?
R is positive.
Right, but we're talking about what if I were negative.
Oh.
Okay, so if I were negative, I told you that we'd shoot through the pole and end up over here. So I want to explain what you wrote on the front side of your notes. Okay, and it said that if r is negative, then your polar point P is going to end up on the terminal side of theta plus pi. Isn't this theta right here? And then plus pi, isn't that plus pi? From here to here is theta. And if I want to keep revolving until I get to the other side of this line, isn't that a total revolution of pi? So that's what I mean by if r is negative, you're going to go theta plus a pi. And that's where your polar coordinate's going to end up. I find it a lot easier for you just to go, okay, here's theta, and I'm going to shoot through the pole and get over here on the other side, if r is negative. But in our case, r is positive, and so we're going to plot just a distance. We're going to plot just on this side a distance of 1. Wouldn't this be a radius of 1 right here at that point? So I'm going to plot a point right here, and that represents P. So there's P. And that point right there represents the polar coordinate 1 pi over 2. Now, unlike the rectangular coordinate that we plotted earlier, 3, 4, where there's only one exact place that all of us could plot 3, 4 and name it 3, 4. There's only one way you name the point 3, 4. It's 3, 4. There's no other way to go about it. However, I have more than one way that I can name this point that we just plotted. So as you look at this point right here, how can I get to that same point again? Can't I go a full revolution around this circle here, a full revolution, and end up back at that same point? Aren't there two ordered pairs that could be the same thing as this? What is pi over 2 plus a full revolution? That's 2 pi. So what would be, so let's write it down. So we have the same r, which is 1. But what if we took pi over 2 and added a revolution of 2 pi to it? In order to do that, don't I have to have 2 pi as something over 2? Don't I multiply this by 2 and this by 2? So that means that this is 4 pi plus a pi is what?
5 pi over 4.
Yeah, so my other coordinate would be 1, 5 pi over 4. So this point, this polar coordinate, can be named by 1 pi over 2, and this point can be named 1, 5 pi over 4, not 4. People, not 4. What is it? It's 2. So this point can be named by both of these. Couldn't I do another revolution again? Couldn't I add another 4 pi over 2 here to make it 9 pi over 2? Couldn't I do this all day long? So how many ways do I have to name point P? Infinite. Kelly? Because if I'm going to add a full revolution to this, because to go from here and add a full revolution would be 2 pi. So we changed 2 pi into something over 2 by multiplying top and bottom by 2. Doesn't that give me 4 pi here plus the 1 pi? Gives me my 5 pi over 2. I could just keep doing that all day long. Keep adding 4 pi over 2, 4 pi over 2. Could I subtract and go backwards? Could I subtract a revolution? Can you shut that door for me? Can I subtract a revolution and end up in the same place? Yes or no? I could. So technically I could add or subtract this full revolution. So how do I show that? Take 1, and couldn't I, and then take my original pi over 2, and I could either add or I could subtract a full revolution. Well, in the past, haven't we used 2n pi to represent the number of revolutions I could add or subtract to show that? What does n represent? What does n mean? How many revolutions I'm going to go, right? So maybe I'll take 5 revolutions. I could go 5 revolutions around, which that would mean I would add 4 pi over 2 5 times, and I would get my proper radian measure here. Or I could subtract 3 revolutions, meaning I could go clockwise, 4 pi over 2, 4 pi over 2, 4 pi over 2. Sorry about that. And that would give me an equivalent point. So I could just keep doing this all day long, but this represents all the possibilities. Now I will tell you that in Math Excel, they don't consider the negative. So when you're doing these problems in Math Excel, and there's not a whole lot of them for you to do tonight, there might be maybe 4 or 5 problems total out of the ones that we talk about that you can do tonight. But don't put in the negative on Math Excel, but on my tests, I want you to put the negative. On your paper, when you write down your work, I want you to put in the negative. Is that clear?
So it's the plus.
You're just going to put a plus into Math Excel, but I need you to understand that we could subtract full revolutions as well. It's important that you realize that. And so if you ignore that, then when it comes time to take my test, you're going to get marked off because you ignored the negative. So I can't help you, your textbook ignores it, but technically you could go backwards. We're going to come back to this because there's another way that we could name this point, and you'll see why in a minute. Let's talk about what happens if r is negative. So let's do the second example, pre-example, and it'll be our unsmiley face example, our sad face. This time we're going to plot -1 pi over 2. So the only thing that's different is that I changed my r to negative. So again, I'm going to draw my polar coordinates with its circles in there. So last time you'll see me drawing the circles. So again, you're going to concentrate on your theta first. Just like the problem that we previously did, this is pi over 2, this one's pi over 2, this is still the same line that our polar coordinate is going to land on. So as I go from 0 to pi over 2, that hasn't changed. So theta is still pi over 2. And this is where our pi over 2 is, here. That hasn't changed. And so I'm going to make that line, I'm going to give it just a little bit of color. So we're going to land somewhere along this line that I'm coloring. Because there has to be a difference between these two, right? So again, if I go from here to here, this is the terminal side of theta, meaning this is the positive side of the line. If I want to do a -1, I'm going to shoot through the pole and end up over on this side of the line, a distance of a radius of 1. So doesn't P end up right here? And so that point there is -1 pi over 2. The only difference is that, and then we can call that P, point P. The only difference between these two graphs is this one has a positive R and this one has the negative R. We still maintain the same theta. Theta never changed. So then my next question is, how can I represent all the possibilities for this point? Because that's not the only possibility. Can't we do the same thing we did over here? If I'm from this point, once I go from here, shoot through here, can I just do full revolutions around and keep getting the same point? True or false? True. Or I could subtract full revolutions and get the same point. So if I were to list out all the possibilities for this ordered pair, it would be -1, comma. Always start with your original theta, which is pi over 2. And from there, I'm going to add or subtract, again, reminder, Math Excel only does addition, to n pi. The n represents the number of revolutions you're going to take. So this represents all the possibilities for that point. But now that we've talked about plotting a -r, what would happen if I changed this -r to a positive r, maintaining the same theta? How am I going to get back to here? Because if I plot this, we're plotting what we had over here, right? So if I plot this, we go 2 pi over 2, there's the terminal side, and if it's +1, then I'm going to plot right here. R is positive. I want to be on the opposite side of the point. So how do I get from here to here? I can't make one negative and shoot through the pole because one's got to be positive. So if one is positive and this is theta, that's my terminal side of theta. But instead, if I can't make one negative, how do I go from here to here? Add what? Add pi, right? Couldn't I just add pi? The distance, and think about this, to go from one end of a straight line to the other end of the straight line, isn't that a revolution or an angle, a direction change of 180 degrees? So if I want to change this point from being here to being over here, all I have to do is add pi to that original theta. And then what that does is it takes me from the polar axis up to theta, which is pi over 2. Then because I'm adding pi, I end up down here at 3 pi over 2, right? And because my r is 1, this is the terminal side of my new theta. This is my new theta. My new theta, that adds to 3 pi over 2, doesn't it? Doesn't it? Yep. So my actual theta here goes from here all the way to here now. And since r is positive, this is my terminal side, which is now the positive side. If one were negative, it'd shoot me through the pole and I'd be up here. So this works. But then I want to be able to go in full revolutions from there to get my infinite number of possibilities. So after I add the pi, then I'll go ahead and add or subtract 2 n pi to get all the revolutions from 3 pi over 2. I personally will accept that as an answer. Math Excel, not so much. I can guarantee you they won't accept that as an answer. So let's talk about what they will accept as an answer. Well, here we go. Let's just look at what we just added here. Just this part we added here. They'll accept this as an answer, just written as is, obviously without the negative. But this right here. So I'm going to take and we're going to simplify just this part right here. Do they have a greatest common factor? Pi. So if I take a pi out in front, what do I have left for the first term?
1 plus 2n.
We have a 1, right? Pi divided by pi is 1, plus or minus, because I like the minus. And then divide this one by pi, you get a 2n, right? So 1 plus 2n. Well, they like to put the pi behind. So when we use this, we're going to actually write it out. So let's write out the one that Math Excel will accept. They'll do the 1 comma pi over 2. Then they'll do plus, and I'll do plus. Then instead they're going to do parentheses 1, I like plus or minus, you're just going to stick with plus in Math Excel, 2n. With the pi behind there, and then a final parentheses. So this is what Math Excel accepts. So we are going to just start to add that. This is Math Excel.
Does it matter if we do that on the test?
I don't care. You can do that on your test too. I personally will accept these ones. I'm jumping up for joy if you can tell me that that's the progression. I'm not going to be picky and make you do all the simplifying. But just let it be known that this right here is what we add on for the second one. So we're going to do our happy smiley face example over here. We're going to get the second set of possibilities, and we'll use Math Excel simplification. But I just wanted you to understand that to go from theta to here, we had to add pi. And that's why we're taking our theta and adding our pi. And then from there, we can add full revolutions. So over here, notice that on this one, didn't we change the sign of r? So to find your second set of infinite possibilities, you're going to always change the sign of r. You're going to keep theta as it is, but instead of adding 2n pi, you're going to add 1 plus or minus 2n parentheses pi. So over here on this one, we change the sign of r, so does not become -1. We keep our theta, but then we're going to add Math Excel's revolutions. So we have to add 1 plus or minus 2n, all of that times pi, and then you end your parentheses. So this is what Math Excel is going to accept. So for Math Excel, you need to learn this part of it. So the first one you add 2n pi, second one you add 1 plus 2n times pi. And again, for Math Excel, you're leaving out these minuses. But the rest, it should look like that. And if you get the answer wrong, they'll tell you, well, it needs to be in this form. So my suggestion would be, don't waste all of your 5 chances by trying to get that form. If you don't get in 2 chances, then stop, and we'll talk about it tomorrow or the next day, whenever we get a chance to get to it.
Just a general question. How many circles do you know to put, like, on the front?
Oh, I just put 4, you know, but if I give it to you to plot, I'll already have the circles there, these circles here. And if Math Excel gives it to you to plot, they already have that polar coordinate system written with the circles in there, so you don't need to worry about that. All right, any other questions before we actually do real example 1? No? None? Okay, so we're going to go back to real example 1. All right, so then again, on the back of your notes here, due to Math Excel's eccentricities, we're going to correct this to read 2n plus or minus 1, and we're going to correct this one to read 2n plus or minus 1, just for your note purposes. But that's where we did our pre-example. So that's the only difference. All right, so then we're going to look at converting rectangular coordinates to polar and polar to rectangular. It's much easier to go from polar to rectangular than it is from rectangular to polar. You'll see why in a minute. We are going to use these following formulas, which technically you already know these. I don't memorize them, but you might want to write yourself a note because in my opinion, you need to do the following. So you need to either learn to derive these or memorize them. And I am not a big proponent of memorization. I don't have them memorized. I have a whole lot more important things that need to be up in my head other than memorizing those things. So I won't give them to you, but you need to know this, 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 and you already know this. So let's talk about how to derive them, because it'll make somewhat perfect sense. So let's go ahead and just put into quadrant 1 a special right triangle, or it doesn't matter, any triangle. And so we're going to have theta, bless you. So theta is going to be here from initial side to terminal side. And then R represents this point here. And then this, of course, is our XY coordinate, which means that this would be our X value and this would be our Y value. I think it's pretty self-explanatory where this formula right here came from, according to this picture. Where did this formula come from? The Pythagorean theorem. So that one's pretty self-explanatory. As long as you realize that if we think in terms of this being in the polar coordinate system, this would be the pole, this would be the polar coordinate, so this distance represents R, the hypotenuse of that triangle. And so that's where that comes from. Obviously, tangent is opposite over adjacent, so according to theta, side opposite is Y, adjacent is X. Well, then these are the only ones you have to derive. And if you think about it, in the unit circle, isn't the X value cosine and isn't the Y value sine in the ordered pairs? So that makes sense. But the problem is if I use a special right triangle, let's say I have a 30, 60, 90, and across from the 30 is 1, and here would be rad 3, and here would be 2. If I just found the sine of 30 degrees, it'd be 1 over 2. But it doesn't take into account the length of this R. And so that's where this R comes into play. So how are these derived? Let's just look to see how that works. So if I were to find the sine of theta, according to my picture, what's the sine of theta? Y over R. And of course, we would convert this into a proportion, and then we would cross multiply and solve. If I cross multiply, I'll have Y times 1 is Y, so there's my Y. And I'd have R times the sine of theta. There's R times the sine of theta, derived, done. If I want to find cosine of theta is going to equal what over what? Everybody. X over R. So same thing, I'm going to convert that into a proportion and cross multiply and solve. So again, I get X times 1, there's your X, and then R times cosine of theta, there's your R cosine of theta. And we already talked about this when we did polar form for a complex number. We talked about this. You may not remember, but we did. And so I don't care whether you learn to derive them or memorize them, it's up to you. You choose. But we're going to use any one of those 4 down below to solve the questions in example 3. So let's go ahead and convert from polar to rectangular. This is the easier way. So I would start off first by plotting my polar coordinate. So if I have a polar coordinate that has a theta of 5 pi over 6 and a positive r, what quadrant is it going to end up in? This brings us to a review from yesterday. What quadrant? Because 5 pi over 6 belongs in what quadrant? 2, right? So if I were to plot this, five pi over 6, bless you. Here is that line. Theta would be from here to here. So theta would equal 5 pi over 6, because this right here is 6 pi over 6. And then if p is 3, that means that I'm going to count 1, 2, 3 units here. So I'm going to plot 1, 2, here's my third unit. This is where my polar coordinate p would be. Then I could create a special right triangle from there. Just bring it straight down to the x-axis. But instead of using theta, won't I have theta prime? Won't this be theta prime right here? And if theta is 5 pi over 6, and this is 6 pi over 6, what's left over for here? Pi over 6. So theta prime is equal to pi over 6, which is what degree? 30 degrees. So we're going to put 30 degrees here. So that's 30 degrees. So then I want to set up my special right triangle. I'm going to ignore r for the moment because it's going to come out when we use the formula. So if I set up my special right triangle, I'm going to use black, I think. So across from 30, wouldn't that be a positive 1? What's across from 60? Negative radical 3, right? And then the hypotenuse is 2. So when I go to find my x and my y, because to get to rectangular, I need an x and a y. So let's start off with finding x first. So x is equal to r times the cosine of theta. Well, I know r. R is equal to 3. Because there's r right there in my polar coordinate. And so then that's going to be times the cosine of a 30-degree angle, because I'm going to use my theta prime because it's coterminal to the 5 pi over 6. So what is the cosine of that 30-degree angle? Yeah, so the cosine is adjacent over hypotenuse, so it's negative rad 3 over 2. So I may not have enough room, so I'm going to... It will not let me erase, seriously. Nope. Alrighty. Negative radical 3 over 2. And then when I multiply the 3 through, nothing cancels out. So I get negative 3 radical 3 over 2. And this should not be surprising, because what value do I expect x to be in quadrant 2? Negative. And it turned out negative, which is fabulous. So then we're going to find y.
So you change the sign.
What do you mean I changed the sign? I did not change the sign.
Cosine 30.
Well, because cosine of 30 adjacent is negative rad 3. So I didn't change the sign. The sign was negative rad 3 over 2. So if you set up your special right triangle with the proper signs according to the quadrant, you don't have to worry about signs. If you don't plot in the quadrant, then you have to think about signs. All students, sign's the only one that's positive, right? So that's why I have a negative.
Because I was like thinking about the unit circle, where what is cosine of 30?
Right, because
So-
you're thinking in quadrant 1.
Yeah,
Well,
or in
our
quadrant.
theta's in quadrant 2, and that's why. All right, so then my y is going to equal r times the sine of theta. Well, again, I know r. R is 3, and then times the sine of 30 degrees. So y is equal to 3 times, what's the sine of 30? opposite 1 over hypotenuse 2. And again, nothing cancels. So y ends up being 3 over 2. Which makes sense because y we anticipated would be what? Positive. And it turned out positive. So then you have to write your answer as an ordered pair. So our ordered pair answer is negative 3 rad 3 over 2, comma 3 over 2. So this is our final answer. Most of that is using prior knowledge, is it not? So it sounds reasonable. All right, then I would like you to do B on your own. So plot 5 pi over 4 in the polar coordinate grid. So figure out what quadrant that's in. Figure out if you have to shoot through the hole, through the pole, or not. And then find your x and y. And I'm going to quietly do it up here without you seeing it. Do you have a question? Come on up. You want to use the rationalized version of your sine and cosine.
So if x is 5, does that mean you get over 5 something?
X is not 5, R is 5.
Oh, okay.
So R is here, but you want to use that later.
Okay.
You want to set up your special right triangle first.
That makes sense.
So when you get an answer, I want you to share it with those around you. So do we think we have an answer?
Yes.
What can you tell me about a 45, 45, 90 triangle?
That sine and cosine are always the same.
Sine and cosine are the same. They might have opposite signs depending upon what quadrant the triangle is in. So what does that tell you about the legs of the triangle?
They're 1 and 1, or they're even.
Well, you know that your x and your y for your polar coordinates are going to be the same number. Again, they might be different signs depending upon what quadrant your polar coordinate started in. But this is in quadrant 1, isn't it? So here's your answer. And I heard somebody talking about the triangle. Did you not know how to draw a triangle? Or where to draw it? What did you mean by that?
I didn't know because like I didn't know it's like because when you found like the first 5 or 4, like you had that like line.
Oh, because it was
yeah.
theta versus theta prime.
Yeah.
In quadrant 1, theta and theta prime are the same. And that's the only time that that occurs. So I don't have to think about theta versus theta prime. So that's a good question. So that's why I just left it as 45 degrees. The minute you leave quadrant 1 and go into 2, 3, or 4, then you have to consider theta and theta prime, because then it's bigger than 90. And so I did write here that cosine and sine of 45 degrees, you should be using the rationalized form, not 1 over rad 2. Because if you use 1 over rad 2, your math is much more difficult in here. And so for both of these, the sine and the cosine were identical. And the r was identical, so doesn't that make your x and your y identical? And you don't multiply the 5 to the denominator. You only multiply it to the numerator only, and so the denominator should be 2. And so these are your coordinates. They're both positive, positive, which makes sense that they belong in quadrant 1. So any questions about that? What do you think the issue with C is going to be? Your reference angle is 20 degrees. And here's why. Negative 200 degrees actually ends up in quadrant 2. Because this is 0 degrees, this is negative 90 degrees, this is negative 180 degrees, well, it's a terrible 80, there we go. And then this is negative 270 degrees. So negative 200 has to be in between 180, negative 180 and negative 270. And so we end up with our polar line going through there, so to speak. And from here to here, from the initial side, which starts at 0 and goes all the way to here, that's the negative 200 degrees. And so that's where Sam is saying that your reference angle here is really 20 degrees in there, because take the difference between 180 and 200, you have a difference of 20 degrees. So it's not a special right triangle. So there's no need to use any of the formulas above. Well, okay, we will use the formulas above. But we're going to use our calculator, right? So all we need to know for rectangular form is x and y. And we know that this is our r, and this is our theta. So why not take the formulas that we were using previously? So let's take our x formula. X is equal to r times the cosine of theta, and let's replace r and theta with their values. So I get x is equal to, instead of r, we're going to put in 2. And instead of theta, we're going to put in negative 200 degrees. We'll put that into your calculator. Put it in exactly as it looks. Make sure your calculator is in what mode? Degrees. And when you put that in your calculator, 2 times the cosine of theta, let's go ahead and round to 2 decimal places. So you're going to get an approximation. So squiggly equals. So you get negative, right? 1 point what? It'll be 88. Does it make sense that x is negative in quadrant 2? Shouldn't x be negative in quadrant 2? Right? Because here's, we forgot to actually plot the polar coordinate, but if I were to go plot my angle first, here's where the negative 220 is. Because r is positive, do I stay here or do I shoot through the hole? You stay here, and you would be mapping out a distance of 2. So there's where your ordered pair is going to end up, your point r. So it makes sense that we are in quadrant 2 and that x would be a negative 188. So then let's find y. So then y is equal to r times the sine of theta. Well, we know that r is still, hasn't changed, it's still 2. And then you're going to put into your calculator sine of negative 200 degrees. You could use your reference angle, but if you use your reference angle, then you have to think about what the sine is for sine and cosine in quadrant 2. Because if you put 20 degrees into your calculator thinks your angle is in quadrant 1. And it'll always give you a positive value. So be careful with that. So then if you plug that in, what do you get? And does it make sense that y is positive? In quadrant 2, yeah. So 0.68, yep. And so your answer is negative 1.88, comma 0.68. So sometimes we will have an estimated answer, but only if it's not a special right triangle. So that wasn't so bad, was it? Not too bad. But let's look at example 4 and then we'll be done for today. So then for example 4, we're going to convert from rectangular to polar. It's a little bit more difficult. And you'll see why as we go along here. So let's go ahead and plot the ordered pair. Negative 1, 1. Doesn't that plot into quadrant 2? So if I were to go my point, negative 1, 1 would be what, right here? And this would be point P, give or take. Let's bear in mind that I can create a lovely special right triangle here. This green distance is going to represent, because this is the distance from R0, 0 in the rectangular system is the same as the pole, where the pole is. And so this distance from here to here represents what in the polar coordinate system? That's your R, isn't that your R? So that's your R. And then I can make this special right triangle going straight down. Well, that's so tiny in here, I'm going to make it bigger if you don't mind. So I'm going to make it bigger over here to the left. So here's this, and really theta is from here to here, and that's very important that you understand that this is where theta is. Theta goes from the initial side to the terminal side where R is. In our triangle, isn't this theta prime? It is not theta. So when we find theta, what are we going to have to do with it? Well, I'm sorry, when we find theta prime, what are we going to have to do with it? We're going to have to subtract it from 180 to see what our theta really is. So keep that in mind. Then, according to theta and my ordered pair up here, isn't my x value negative 1 and my y value is 1. So my x value here is negative 1. My y value is positive 1. Which should tell you right now what theta prime is. It's a 45-degree angle because x and y are essentially the same number, they're just opposite signs. But we'll get to that in a minute. We still have to find r. Yeah, we still have to... Yeah, but that's only because our sides are 1 and 1. That's why it's the square root of 2. But we'll come up with it on our own without that. So we're going to use, finally, the formula that you see above there for r. We're going to find r first. So we've got r squared is equal to x squared plus y squared. And that's just using Pythagorean's theorem. So, you know, as you, all of, or several of you in here guessed, we know theta's 45 degrees. Well, that's theta prime. And we know that r has got to be radical 2. But what if the side lengths were 2 and negative 2, or 3 and negative 3? Some of you still can calculate that quickly, and that's okay. But what if we didn't know that? Let's go ahead and use our formula anyway. Whoops, I don't want y there. Good thing I'm not a doctor. All right, so then our x is negative 1 and our y is 1. So that leaves us with r squared equaling 1 plus 1, r squared equaling 2. Now here comes the problem that you will have missed if you had just used your guesses before, or your educated guesses based upon experience. How do I solve for r? Take the square root of both sides, but technically don't we do plus or minus the square root? That's a square root. Shocking but true. Don't we do plus or minus when we take the square root of both sides? When we did that in the rectangular system, we ignored the negative because we said the hypotenuse could never be a negative value. But in the polar coordinate system, can r be negative? Ah, Yes, it can, right? So now this is what makes it harder. R can be both positive or negative square root of 2. So we have 2 answers that we have to come up with. And technically, there are an infinite number of answers you could supply me with. But let's try to keep our answers between 0 and 2 pi, or between 0 and negative 2 pi. I beg of you. That would make my life a whole lot easier, and you want me happier when I'm grading your problems. All right, so let's just start off with our theta. So if theta prime, which we are correct in the fact that theta prime is equal to 45 degrees, then theta is equal to 180 minus that 45 degrees, right? Which leaves us with what? 135 degrees. Couldn't we have gotten that by using tangent? Right? We could have used, instead of doing this, we could have used tangent of theta is equal to 1 over negative 1. We definitely could have done it that way as well. Because if I don't know that this is a special right triangle, then I'm going to have to use tangent. So you might want to write yourself a note, could have used tangent. Okay? So using these 2 possibilities, let's start with theta, and 135 degrees is what in radians, because we want our theta in radians. Well, if it's over 4, then isn't this 4 pi over 4? And if this is 4 pi over 4, and this angle here is pi over 4, what's 4 pi over 4 minus pi over 4?
3 pi.
So there's our radians, 3 pi over 4. That's what I'm going to use for my theta. So here's my 2 answers. One answer, let's just start with 3 pi over 4. Because I don't know if connected to 3 pi over 4 is a positive or a negative rad 2. So let's plot it. If I go from initial to this side, which is 3 pi over 4, do I want to stay here, or do I want to shoot through the hole and be over here? Where's my rectangular coordinate in? What quadrant? This quadrant right here, so I want to stay here. So if I go from here to here, which is 3 pi over 4, I want to stay here, right? I don't want to shoot through the hole to the other side of the line. So if I want to stay here, will R be positive or negative? To stay there, R would be positive. To shoot through the hole, R would be negative. I don't want to shoot through the hole. I want to stay there. So R is going to be positive. So I'm going to choose my positive value here to go with the 3 pi over 4. So my positive value of rad 2 goes with the 3 pi over 4. So then what goes with negative radical 2? So if I have a negative radical 2, and remember this line here extends over into quadrant 4, doesn't it?
Why is it negative?
Why isn't what negative?
Why is it 2?
Because remember R can be both positive or negative? Well, we already used up our positive.
Oh.
So now we have to use up our negative. So let's think about this. If this is negative, which we can't change that, that means if I'm over here, I'm going to shoot through the hole and end up over here. But if I'm over here, I'm going to shoot through the hole and end up over there. So where do I want theta to bring me? Up here or down here? Down here, because I'm going to shoot through the hole, and that's where I want to end up at. I'm shooting through the hole because my R is negative. So if I want to get here, what's a way for me to get here? I could do 7 pi over 4, right? Because Sam said that this is 8 pi over 4, which is correct. Or I can view it as 0, right? Remember I told you that you could go from 0 to negative 2 pi. You could go backwards. I'll let you do that. So I could go backwards, couldn't I? So I could do 7 pi over 4, which is just shy of a pi over 4, because this value right here is pi over 4. So this could be 7 pi over 4. It's a totally viable answer. Or I could go backwards, and so since I want you to consider negatives, we're going to go backwards. If I go backwards, what's that value of theta? Negative pi over 4. So that means that negative pi over 4. So let's test it. if I went negative pi over 4, that means I go clockwise. So I end up right here. And then because my r is negative, won't I shoot through the hole over here? Right? Didn't it work? I went from 0 to negative pi over 4, right to here. And then because my r is negative, from here I'm going to shoot through the hole to the other side and count out a distance of radical 2. And that's where I want to be, so it works.
And then from where did you get the pi over 4?
The negative pi over 4.
Yeah, the negative.
Well, I got that because Sam, we talked about this, right? So Sam said, couldn't we go from here all the way to here to get to that side? Because we determined we want to be on this side because if r is negative, it's shooting us through the hole, right? So we could go from here all the way to here, which would be, from here to here is 4 pi over 4. 5 pi over 4, 6 pi over 4, 7 pi over 4. So you could have put positive 7 pi over 4 here, and with a negative r, it's going to shoot you through the hole, right? Or instead, I want you to think that we could go negatively. So if I went backwards this direction, isn't that a negative direction? So I could go negative pi over 4. That puts me in the same exact coterminal place as 7 pi over 4.
So I can use 7 pi over 4 as well.
You could use 7 pi over 4 as well. But aren't there an infinite number of possibilities that you could give me for this? But let's keep them in between 0 and 2 pi and 0 and negative 2 pi for my peace of mind. Because that cuts down the number of possibilities you could give me. MathXL for this question is question number 15. And they're going to give you a list of choices that you choose from. And you click on all the choices that are possible that work. And so what I would do would be to plot. I'd try to figure it out algebraically because you're going to have to do it on your test that way. But then you could also figure it out graphically by plotting it and choosing which one's correct. All right, so let's look at the second one. This one's interesting because look at what happens when you plot that coordinate point. Where does it plot?
Just 1 point.
It's on the x-axis, isn't it, right? So that plot, that points, if this is negative 3, this is positive 3. That point plots right here. So theta goes from here to here. What is theta? We can tell what theta is immediately. What's theta? In radians. How far did I go from here to here? Pi, right? It's just pi. So theta is pi. I don't have to use a triangle. Plus, I can't even make a triangle if my point is on an axis. Not really. And so I know theta, I have to find r. So we're just going to use our formula for r. R, once you find it, you're going to go, oh, that was obvious. But again, if you use the obvious, you're going to miss one of your answers. So remember, r squared is equal to x squared plus y squared. On my ordered pair here, this is my x and this is my y. So r squared is equal to, we're going to plug in our values for x and y. So my x is negative 3 and my y is 0. When I plug in negative 3, I get r squared is equal to 9 because 0 squared is 0 added to negative 3 squared is 9. When I solve for r, what do I get? Plus or minus the square root of 9, which is plus or minus 3. So I can have two different answers for r. So again, let's start with theta first, because my theta is going to change also. So let's start with the theta that we just found. So we're going to start with theta of pi. We have to decide, does a positive 3 go for r or a negative 3? So let's walk ourselves through it again. If I go from the initial side to the terminal side, theta here, boom. Do I want to stay here, or do I want to shoot through the hole?
Stay.
I want to stay because that's where my point is. So if I go from here to here, and I want to stay there, what does r have to be, positive or negative?
Negative.
I want to stay because if r is negative, I'm shooting through the hole. So if I want to stay, r has to be positive.
Wait, explain that again, sorry. I lost it.
If I go from here to here to pi, isn't that where my point is? So I want to stay here. If r is negative, I'm going to shoot through the hole. I'm going to go away from it. Right?
Yes.
So I want r to be positive because I want to stay here.
I don't get that. Why are you saying positive if it's something negative?
It has nothing to do with 3 being negative. It has everything to do with, do you want to stay here or do you want to move over here? Because once you do the rotation, because we always plot the rotation first. The rotation goes from here to here, which lands us exactly where I want to be.
But that's -3. Why?
It's not, you've got to take away the x and y coordinate system. So you're right here. If, and we're going to now plot the distance from R from the pole to here, because I'm in this quadrant, right?
Oh, we're doing it from the pole. That's what.
It's always from the pole. I mean, technically, I don't know what my radius is, right? I don't know what R is. So I could be going from here to here, and I have to plot a distance out of 3. The negative isn't a distance per se, it's a directed distance telling me what direction I'm going to go from the pole. So technically from here, if it's negative, I'm shooting the opposite direction from where I am. That's why I don't like to be at the pole, because it's hard to tell am I on the left side of the pole or the right side of the pole. So I moved you from here to here. I just happened to put it right at 3. Couldn't I have moved from here to here? Because I don't really technically know what my R is yet, because I haven't plotted it yet. So if I move pi, that moves me from quadrant 1 to quadrant 2. I want to stay in quadrant 2 because the point I'm looking for is in quadrant 2. Since I want to stay in quadrant 2, R had better be positive. Because if I make my R negative, it means you're shooting through the hole to the other side, and now you're over here. And my point is not over here, it's over here. Does that make sense now? Okay, so that's why we're choosing +3 to go with pi. So here's something that looks like it should belong in quadrant 1 because the R is positive, but it doesn't. Redraw it again. We're going to start here at pi, so we go from 0 to pi, and then because R is positive, we stay here and move a distance from the pole of 3, and there we end up at what appeared to have been -3 in the rectangular coordinate system.
Is R going to be always like positive on the first like over here kind of thing?
No.
No.
Oh, you mean the first one? The way we're finding theta? Yes. She wanted to know, will R always be positive here? The way we're finding theta originally, my answer to that is probably yes. The way I'm showing you to find theta. Because we want to stay there. Does that make sense? Mm-hmm. Okay. So then I know that my other R has to be -3 because that's my other choice. So then we have to decide what is theta going to be. So let's think about this. If R is negative and I land here, won't the negative shoot me over here to the left? If theta lands me on this side and R is negative, it'll shoot me through the hole over here. If theta lands me over here and R is negative, because R is negative, I can't change that, it'll shoot me over here. Since I want to be here and R is going to shoot me in the opposite direction, don't I want to end up in the opposite direction after my rotation? In other words, I want to be on the opposite side after my rotation because R is going to shoot me through the hole. So if I'm going to get shot through the hole, I'm going to go from the right to the left, don't I? So what value of theta puts me here to begin with? Thinking from 0 to 2 pi or 0 to -2 pi. So over here is 0, or it could be 2 pi, or it could be -2 pi, couldn't it? Well, those are all values at that point, isn't it? At the initial side. So if you chose 0, -2 pi, or 2 pi, along with the -3, you're going to be good to go. Because, look what happens. If I choose 2 pi, that means I went from here all the way around back to here, right? And then you would plot your directed distance of -3, which shoots you through the hole 3 away from the pole. Isn't that where I want to be? Same thing happens. If I start here at 0, it means I go nowhere, rotationally. And I still shoot through the hole at -3. And if I did -2 pi, it means I'm going to go backwards to 2 pi, or backwards to here, and I'm going to shoot through the hole. So any one of these would work. I'm going to just go ahead and write 0. But you could have used any of those 3. So, and we could do this over and over again. But in my parameters from 0 to 2 pi and 0 to -2 pi, those are the 3 that would work. Yes.
So for the -3, basically you want to start wherever the point is. And go to the
For
other
the
side.
negative, you want to start on the opposite side. So if your R is negative, you want to, after your rotation, you want to end up on the opposite side of where you want to be. Because when R is negative, it's going to shoot you in the opposite direction. So when your R is negative, think I need to be on the direct opposite of where I want to end up at. And that'll help you figure out where theta should be. Okay? So we're going to convert polar equations to rectangular equations and vice versa. So yesterday we were converting polar coordinates to rectangular coordinates and vice versa. So today we're working with equations. And mostly so that we can be able to put them in our calculator and graph them. And we'll be doing graphing tomorrow. So I want you to recall, so to the right, I'm going to write the following equations that we've used in the past. And so it's really from your previous note page. What does r squared equal? Oh wow, that's really fat. Hang on. I don't want such a fat pen. So r squared is equal to what? Oh, no. And look at the equations on the other side. Isn't it x squared plus y squared? Which actually, if you think about it, isn't that the equation of a circle? At 0, 0 with radius r. It also is the magnitude prior to having the square root taken care of, having us take the square root of it. It's a lot of different things. All right, what does x equal? R times the cosine of theta. And what does y equal? R times the sine of theta. And then also we can use tangent of theta is equal to y over x. So those are all equations from the previous note page, correct? We're going to use all of these, or not all of them, but we're going to use some of them as, I think I'm going to use, let's see. We're going to use some of these here as just direct translations. I'm going to get rid of any of my trig functions and my r. And I'm going to get totally to x's and y's. So if I have an r squared, I can replace it with x squared plus y squared. If I have an x anywhere, I can replace it with r cosine of theta and a y with r sine of theta. And if I have a tangent, I can replace that with y over x. And of course, vice versa. So let's start here. I see an r, but I don't see an r squared. I don't have a direct translation or direct substitution for r. And I also see secant. Carly, can you shut the door for me, please? Sorry. So if I don't have secant over here, what have we done in the past with secant to get rid of it? Okay, so if you have secant, cosecant, or cotangent, please do yourself a favor and use the reciprocal functions to get rid of it. So that's where we're going to start. I'm going to start with r equals 4 times, instead of secant, we're going to put in 1 over the cosine of theta. So all we did was replace secant of theta with 1 over cosine of theta. So that leaves me with r equals 4 over the cosine of theta. Well, I still don't have a direct translation for just cosine. And I don't have a direct translation for just r, but do we like ugly fractions? So if you have a fraction, my suggestion would be to get rid of it. And so we're going to get rid of this fraction by doing what? Yep, if I multiply this side by cosine of theta, put that over 1, then I would have to multiply this side, I'm going to squeeze it in here, by cosine of theta. So magic occurs here. When I multiply, forgot I put that on the lightsaber, it startled me. When I multiply the r and the cosine of theta together, I get r cosine of theta, and I always prefer to write the r in front of my trig function. And then, of course, my cosines here cancel, and I end up with an equals 4. And this is where the magic has occurred. What does r cosine of theta actually equal? X. It is a direct translation right here. I'm substituting in for r cosine of theta its value for x. And so this whole side goes away and becomes x equals 4. Haven't I successfully gotten rid of all r's and all trig functions? So the question is, what is this the graph of? X equals 4. How would you graph? If I said graph x equals 4, take your brain out of the polar coordinate system, and because you're now in rectangular, you're now in the Cartesian coordinate system. How would you graph x equals 4? It's a vertical line going through what axis? The x-axis. So this is the graph of a vertical line going through, because I'm going to ask you these questions, the x-axis at 4. And then when I'm done, I'll show you how to put these into your calculator using the polar function. All right, so then let's go to problem B. So the issue with problem B, well, I do have a cosine and I have an r, but there's no way to make them come together as r times the cosine of theta. Because if I subtract 4 cosine of theta from both sides, now I have r minus 4 cosine of theta on the left and 0 on the right. That doesn't do me any good. If I divide by cosine of theta to get the cosine over here, now I have r over the cosine of theta, which is not a direct substitution. So instead, I need to be able to do something to this equation to get something over here that I can substitute in for. Is there any way that I can get an r squared here? We could square this side and we could square this side, but then I'm stuck with 16 and cosine squared theta, which I don't have a direct substitution for. So instead, couldn't I, to get an r squared, couldn't I just multiply this by r? That's legal, isn't it? So long as I do what? Multiply the right side by r, as that was an r. Shocking but true. Let's do that again. So I'm going to multiply the right side by an r. And then some magic actually occurs. On the left, I get r squared, which I have a direct substitution for, equals. And I prefer to write this as 4r cosine of theta. You always want the r in front. So 4r cosine of theta. So what does the r squared substitute for? X squared plus y squared equals, and then my r cosine of theta substitutes in for what? It's the same exact here as x, right? So we're going to replace this with x, but not the 4. So the 4 stays the same, and only the r cosine of theta gets replaced with x. So we have successfully gotten rid of all r's and all trig functions, but it's not in proper form. Do you know what this is the equation of? An x squared and a y squared. A what?
X squared and Y squared.
Yeah, an x squared and a y squared. What does that give you? What? A circle. It's exactly what it's going to give you is a circle. I will promise you that right now I will not give you a hyperbole or an ellipse. But because you've had the standard equation of a circle in Algebra 1-2 and in Algebra 3-4, I feel comfortable that you should know it. So let's talk about standard equation of a circle. So that would be x minus h squared plus y minus k squared equals r squared. And that would be where the center is what? What would be the center of this? Yeah, you want to take whatever's being added or subtracted to x and y, that becomes your x and y for your center, and you take the opposite sign. So we're going to take h and k, and so we end up with h comma k. And then the radius is just r. And so that implies that you're going to take the square root of whatever number is here. Whether it's a perfect square or not, you'll take the square root of it to get to r. So we have to get this in this form. That implies we're going to complete the square. So the fun has just begun. So I'm going to move the 4x to the left by doing what? Subtract it. So the 4x is going to move to the left, and it's going to be right behind the x squared. And so we're going to get the following. X squared minus 4x but I'm going to put a plus blank here because we're going to complete the square, and then plus the y squared equals a blank, because if I add a blank to the left side, I have to add a blank to the right side, and there is nothing left on the right side because I moved the 4x by subtracting it over here, and there's nothing left, so it's got a value of 0. Do you remember how to complete the square? Okay, so you're going to take b, you're going to divide it by 2, and you're going to square it, and then that's going to go in your blank. So fortunately, we only have to complete one square here because there's no y term. And so when there's no y term here, we don't have to complete the square. But here we will. So we're going to take 4 in place of b, divide it by 2. So what's 4 divided by 2? Squaring it. What do you get? What do you get? 4. So I'm going to add a 4 to the left and add a 4 to the right. And what you have just created here is a perfect square trinomial that factors into a squared binomial. So the whole purpose of completing the square was so that we could get this nice squared binomial. Question?
Isn't b negative 4 though?
It doesn't matter that b is negative. You can still put the negative in there. I usually ignore the negative because when you square it, it's going to be compositive anyway. So 100% of the time, this constant here, whoops, I forgot I was not on pointer. So 100% of the time, this constant here will always be positive. And it doesn't matter what that sign is. But that's a good question. All right, so we're going to write our binomial. And to factor this, you're just going to take each of your bookends right here and take their square roots. So what's the square root of x squared? X. And the square root of 4? 2. So the x and the 2, the square root of these bookends, that's what I put here. And then how do I determine the middle sign here? Well, whatever the middle sign is in your trinomial, that's the middle sign in your binomial. So you get something from every term in this trinomial. Every term in this trinomial gives you something down here. So each of the bookends you took the square root of and you got those. And then you took the middle sign from the middle term to get the middle sign in your binomials. And then all that's left is to do plus y squared equals 4. And so this becomes our standard equation of our circle. What is the center of this circle? Change the sign. So instead of negative 2, it should be positive 2. And then what's being added or subtracted to y? Do you see anything being added or subtracted? If you had just a plain y squared or just a plain x squared, then that value is 0. So we're going to put here positive 2, comma 0. And so this is going to be a circle that has center at 2, 0. And what is the radius?
2.
And you got that by taking the square root of 4, which is where he got the 2 from. And so we'll do this on your calculator in a minute. So at this point, I'm going to move to an extra sheet of paper and give you some additional problems to do for example 5. So you're going to write yourself a note, C, additional problems on next slide. All right, so continue with example 6. We're now going to convert from rectangular to polar, which actually you'll find this easy now. We're going to get rid of any x's and y's, and we want only r's and trig functions. Is there a direct substitution for x? R times the cosine of theta. Is there a direct substitution for y? What? R times the sine of theta. So that's what we're going to use. So we've got 3, and instead of x, I'm replacing that with r cosine of theta plus 4, and instead of y, we're replacing that with r sine of theta equals 2. So then we're going to rewrite it so that it's written all together. So I've got 3r cosine of theta plus 4r sine of theta equals 2. Now typically we like our polar equation solve for r equals. And so I have two terms that have r in them. These two terms right here. So can I factor out an r out of both of them as a GCF? Even if the 3 and the 4 had a GCF, you wouldn't want to factor that out. So at this point, all you want to do is factor out the r so you can get that r almost by itself. So I'm going to take this r here and this r here, and I'm going to factor it out in front of parentheses. So this whole thing gets divided by r, and this whole thing gets divided by r. Well, not the two. And we're left with, because the r's here cancel, we're left with 3 cosine of theta plus 4, the r's here cancel, sine of theta, equals 2. So if I'm solving for r, how do I get r by itself? Yep, divide this side by 3 cosine of theta plus 4 sine of theta. And divide this side by 3 cosine of theta plus 4 sine of theta. And we're left with r equals 2 over 3 cosine of theta plus 4 sine of theta. And doesn't that look like the very last problem that we just did in example 5? Problem E that I gave you? And if you look at the original problem in rectangular form here, isn't this a linear equation also in standard form? And so we ended up with an equation that looked like this, which is very, very similar to example 5E. All right, so you good with that? Let's look at...
You get 4 sine 2.
Well, when I divided both sides by this, right, nothing here cancels. So this 2 is already over there from before, from the original problem, right? And then this is just that coming over here as a denominator because I'm dividing. Is that okay? Okay, so then let's look at example B. So example B, what is what's the original graph of? A circle. So we're going to get it into polar form. So I have to get rid of the x's and the y's. I could use a direct substitution like we did here for the x's and the y's, but I don't want to square that. I certainly don't want to get a sine squared and a cosine squared in there. So instead, you need to expand this out properly and expand that out properly. And what I mean by properly is, and we've talked about this a lot of you are going to tell me that this squared is x squared minus 9, or you'll tell me it's x squared plus 9. And it has a middle term. So do yourself a favor, take the extra step and write it out longhand so you don't make that error. And so we're just going to FOIL. So I've got x times x is x squared. And then I have x times negative 3 is negative 3x, and negative 3 times x gives me negative 6x, and there's your middle term. And then finally, I have negative 3 times negative 3, which is a positive 9. So don't miss out on that middle term. And on the next one, I've got y times y, which is your plus y squared. And then I have a y times negative 2, which is negative 2y, and a negative 2 times y, which is another negative 2y. Added together gives you a negative 4y. And then finally, negative 2 times negative 2 gives you positive 4, equals 13. So at this point, you just get in the habit of collecting your terms the following way. Knowing the equations that I have for substitution, I want to get the x squared and the y squared together. Why? Because they together are r squared. And so I want to put those together, and then I have a direct substitution for x here, a direct substitution for y there. And another magic occurs. What do you think 9 plus 4 equals? And usually in these particular problems, to make life on you easier, they're going to make those two constants add up to that constant on the right. And so that should cancel out. So we're going to end up with x squared plus y squared minus the 6x minus the 4y. I'm going to add the 9 and the 4 together, which is 13, equals 13. And then we're going to cancel out the 13s, because if I were to subtract 13 from both sides, I would get 0. They'd both cancel out. And then on top of that, we are going to substitute in, oh, I don't want to use green. All right, we're going to substitute in for what? For x squared and y squared again? What are we putting in? R squared. And then minus 6 times, it's probably not big enough. So what am I putting in here for x? R cosine of theta. And then minus 4 times, instead of y, we're going to put in, yep, r sine of theta. I'm going to squeeze that in here. Equals 0. So the right side is 0. And so we're almost there. We have r squared minus 6r cosine of theta minus 4r sine of theta equals 0. So we want to solve for r. So it's generally a good idea to get r squared by itself first. So I'm going to move this term and this term to the other side. How? I'm going to add them. So I end up with r squared is equal to a positive 6r cosine of theta plus a 4r sine of theta. I just added them to both sides. Now you're likely to think that we should do what to solve this? To get r by itself. Square root, right? And that makes sense. I'll just take the square root of both sides. I'll have plus or minus the square root of the right side. Because technically in the polar coordinate system, r can be negative, right? But no, of course not. This is one of the few times you're going to see me dividing by a variable. If I want to solve for r, can't I divide that by r? Well, if I divide that by r, we can divide that by r and that by r. So if I divide one term by r, I have to divide all the terms by r. Technically, I'm dividing that whole right side by r. And we end up with r equals, the r's here cancel, and you get 6 cosine of theta plus the r's here cancel, 4 sine of theta. And you finally have it solved for r alone. And this is a circle, right? Go back to example 6. What does this, which question does this look like in example 5? A, B, C, D, or E? It looks like D, right? The original equation for D, it's very similar to that one. And so it makes sense that we would have solved it this way, because they both should be giving us similar answers. All right, so any general questions over what we did today? Yes?
So what happens to the negative 6?
Remember, we added this to get it over to the right side. Anytime you move a term from one side to the other, it essentially changes signs because you're going to add or subtract it. So when I move, I didn't change the r squared stayed here. I chose not to write plus a 6r cosine of theta plus a 6r cosine of theta. And then plus a 4r sine of theta plus a 4r sine of theta.
We moved the whole thing.
Right. When I move this over to the other side, it changes signs.
Okay, yeah.
Right? Was that the other question that we had hand raised? I saw a couple more.
Well, yeah, I can answer mine, because I thought I was trying to figure out what you did with the 6x, 4y, because I moved them first before.
Oh, okay.
That's why.
Oh, you moved them first.
Yeah, I
Okay.
moved them before.
And you can do that.
Okay.
Yep. Any other issues, problems, concerns? Nope. Okay. All right, so this is going to be example 5 still. But this will be C. I don't think that was enough practice for you. So this one I want you to do on your own. I want you to convert the polar equation to the standard equation. So look at the notes that you just took. You've got r equals 7 times the secant of theta. And while you're working it there, I'm going to quietly work it up here to where you can't see it. So follow your notes. So share your answer with those around you. In addition to that, I want you to share what kind of graph this is going to be.
And then vertical.
Yeah.
So what do we get?
X equals 7.
Yeah, we did not get 7. We got x equals 7 because we're not getting a solution. Although this one looks like a solution, we are getting an equation. So we converted the polar form of r equals 7 secant of theta into the rectangular equation form x equals 7. And so this was just like A, wasn't it? Identical? All right, so let's do another one. D. This one, r is equal to 4 cosine of theta plus 8 sine of theta. A little bit more complicated. Do I have any direct substitutions? Do I have any r squareds? Do I have any r cosine of thetas? Any r sines of thetas?
You take the GCF.
They do have a GCF of 4. Is that going to help us if we took out a GCF of 4? You're right, they do. I never want to convert to tangent.
I don't know that now. I don't think it will.
Look at example B.
Did you divide?
We could divide, but it'd get ugly. What did we do in example B? We multiplied by r. Why? Because I wanted to force an r squared in there. So if I multiply the left side by an r, it forces an r squared in there, and magic is going to occur on the right side as well, because that means I want to multiply this entire side by r as well. And then this r is going to have to be distributed to both terms, the 4 cosine of theta and the 8 sine of theta. So when you actually simplify that, you get r squared is equal to, and I prefer to write this r here when I distribute it in between the 4 and the cosine, because I always want it in front of the cosine. So you're going to get 4 r cosine of theta plus 8 r sine of theta. And here's where the magic occurs. What do we sub in for the r squared? X squared plus y squared equals, what's my next substitution? Yeah, the r cosine of theta, not the 4, but the r cosine of theta has a direct substitution. So we have 4 times, and instead of the r cosine of theta, that gets replaced with x. Then plus, what happens with the r sine of theta? Yeah, it gets replaced with y. And so what is this going to become the graph of? A circle. So it is just like B, but it's a little bit more complicated because this time, I'm going to move this up, this time I have both an x term and a y term. And so we do still have to complete the square. So I'm going to move this x term to the left by subtracting it. I'm going to put it behind the x squared. I'm going to move the 8y by subtracting it and move it behind the y squared. So I will have nothing left on the right but 0. So here's how it's going to look. X squared, or not plus, minus 4x. But I am going to put a plus blank. Why? I'm going to complete the square. Then plus y squared. I'm going to subtract the 8y, so minus 8y. I'm going to put another plus blank because I want to complete the square for that one. And then equals, I have nothing left on the right side, but if I have these 2 plus blanks, then I have to have a blank plus blank on the right. I have to have a blank for every square I'm completing on the left. I have to have that on the right. So we're going to complete the square for this one. So we're going to take b, which is 4, and you can make negative 4 if you want to. Divide it by 2 and square it. What do you get? 4. So I'm going to put a 4 here and a 4 there. Here a 4, there a 4, everywhere a 4, 4.
So is B -4 or 4?
Technically B is -4, but remember I said I just ignore the negative because it's always coming out positive. So you can put the negative in there if you want to, but it should come out positive. And I find that when you guys put the negative in, that oftentimes you will give me a negative answer for that blank. And it should always be a positive answer. All right, so then we're going to complete the square here. So we're going to take the 8 or the -8, it's up to you, divide it by 2. And we're going to square that. What does that give me? So a 16 here and a 16 there. Then we're ready to write out our squared binomial. So we get a squared binomial for the first and a squared binomial for the second. What's 4 plus 16? So the right side is equal to 20. So we're going to go ahead and write out our factoring for this because it's now a perfect square trinomial. What is the square root of your bookends? Square root of your bookends. X and 2. And then what's your middle sign? The same as the middle term, right? So it's a minus. And then what is the square root of these bookends for this next trinomial? Y and 4. And then what's the sign of the middle term? Negative, so we put a negative there. So now this is in proper standard equation form for a circle. So this is the graph of a circle. With center, what's the center? Yeah, because you want opposite signs, right? So 2, 4. And radius? Well, you take the square root of 20. What's the square root of 20? Simplified. Yeah, so this is 4 times 5, so it's 2 rad 5. Totally doable, right? Maybe. All right, then the last one we're going to do is E. Yes?
Are we going to have to, when we have this on the test, we're going to have to write center and radius?
Yes. I fully expect that you should be able to do that. Because it's now the 3rd year in a row you've had it. It's easy. If you can get it into standard form, isn't it easy to read? Right? Once you get into standard form, you always do the opposite of these. X value of the center goes with X. Y value of the center goes with Y, and we use opposite signs. And then take the square root of the constant that's on the right. Yes?
So whenever you don't automatically see something that you can substitute, do you recommend just multiply by R?
Oftentimes. Not automatically, but oftentimes. So the last problem I'm going to do with you is a time where I won't, and you'll see why. So can I move to the next page? Yes? Yes? Okay. So then, because I don't think I have room on here. Maybe I do. Hang tight. I learned a new feature. So now, oh, wow. Hang on. Really? All right, well, I'll play with that later. All right, so next slide. It won't let me move everything. Sometimes technology is not all it's cracked up to be. Okay, so example 5. E. And this is the last one we're going to do for this one. All right, so this time we have something that's even more complicated, but it actually is fairly simple to solve. So you get 4 divided by 3 cosine of theta plus sine of theta. So Chase asked a good question. Do I just automatically, if I don't have a direct substitution, multiply both sides by r? Well, in this case, is multiplying both sides by r, you'll get an r squared on the left, but what does it do on the right? It'll give you a 4r in the numerator, which doesn't help you. What is glaringly irritable about this problem from the beginning? It's a fraction. We don't like fractions, do we? So my suggestion would be to get rid of that fraction first. So how am I going to get rid of the fraction? I don't want to change it to its inverse, but I want to,
Multiply by the.
yeah, always multiply by the denominator. So the denominator is 3 cosine of theta plus sine of theta. So I'm going to multiply this whole side by that, but I also have to multiply the whole left side by that as well. So I don't have a lot of room over here, so I'm going to write it underneath here, but I've got 3 cosine of theta plus sine of theta. So all of this, the r, is going to have to get distributed to both of those terms, and that's where the magic occurs. So when the r gets multiplied or distributed to each of these terms, you're going to write the r in front of the trig function. So we get 3r cosine of theta, there's magic there, plus r sine of theta, there's magic there, equals, and then over here, pardon?
Too much magic.
It's never too much magic. And then these cancel out, and you're left with a 4. What magic occurred here? So that becomes 3x. And what magic occurred here? So that's just plus a y. Equals 4. You should recognize that. What is 3x plus y equals 4? All right, so how do I get negative 3x here? What did I do? I just subtracted 3x from both sides. So that is the graph of a line going through the y-axis where? Y-axis. Yeah, 4 is the y-intercept. So at 4, with a slope of what? Of negative 3. All right, so that's all I have for example 5. Any questions on those before we go in the reverse from rectangular to polar? Say it isn't so, right?